I'm speaking on behalf of Robin Purhouse. We'll give most of this talk, and we want to acknowledge several of our collaborators. But this work is called Inverse Generative Modeling of Alcohol Use Behaviors. And, UNMA, I think this is a good example of where people can adopt injurious behaviors, even knowing they're injurious. So it's a good place to apply that trade. Anyway, the work is being published in a paper with all of us as authors toward inverse generative social science using multi-objective genetic programming. That's in the GECKO proceedings from last July. And it's all part of a much larger project, the Cascade project, which is an R01, an NIH R01, that is, the acronym is from Calibrated Agent Simulations for Combined Analysis of Drinking Etiologies. But given that it's about drinking, the proper acronym would certainly have been Cascade with a K, but we blew it, so oh well. We'll talk about a tiny bit about inverse generative social science because we've said a lot about that already. Then present an agent model, social norms and drinking behavior. Talk about the model discovery methods that were employed, evolutionary programming, and some findings and conclusions. Again, I mean, we're looking for generative mechanisms, mechanism-based agent models that generate observed macro level or meso level or other kinds of data. If you didn't grow it, you didn't explain it. If I can, a tiny aside on this topic that came up yesterday. I mean, the idea of you didn't grow it, you didn't explain it, is a model-free characterization of a particular type of explanation. It's not a diktat saying you can't, what you're allowed to include in your models, right? I mean, you may include all kinds of things in the model that aren't generated in the model, and we do that all the time. We don't grow the actual sugarscape or the Anasazi landscape, and those are not generated. So that's fine, but not everything has to be generated, and there may be mesoscale entities, the Federal Reserve, what have you. Two cases, to the extent that their outputs, like policies, are driven by member-agent interactions, then the member-agent rules are part of the micro-specification in the first place. And if they're not, then it too is exogenous. But the point is, it's not an insistence on, the only things you're allowed to include are things that you generate in the model. Inverse generative social science, of course, is about enlarging the search space of generators and searching it for the best candidates, where best, as we will discuss, could be sheer accuracy, it could be comprehensibility, and we'll show a nice, I think, interesting trade-off curve between those. All right? And the motivation, of course, is that, there may be many ways to grow it. And I think of inverse generative social science as a way of harnessing AI, machine learning, evolutionary programming to the construction and search of those spaces. So here's an example of that enterprise. And Robin, maybe you should go ahead and talk from here.
Thanks, Josh. So just to say a little bit more about the overall aim of this work. So in the end, it's designed to inform policy, alcohol policy, here in the US. What you can see here are some epidemiologically relevant time series that would relate to or be associated with alcohol-related harms, things like liver cirrhosis, alcohol poisoning, about 50 different health conditions that are related to alcohol. The one on the left here, this is the prevalence of drinking. So these are the actual rates of drinking in the population. These are people who are having any kind of alcohol, a drink at least once a year. The upper line is males, and the lower line here is females. So males tend to drink compared to females. So the one in the middle, this is the number of drinking occasions per month, again for males and for females, and this is going from about 1980 here through to around about the year 2000. This is the window we use for our calibration routine. So we have data out to about 2016, but we reserve that for validation. And then over on the right here, we've got the average amount of alcohol consumed in grams of ethanol per drinking occasion, again for males on the top and for females on the bottom. And this is what we're trying to explain. So we're looking for explanatory models that can reproduce these trends. These trends themselves are not without issues, so the data that underpins this is not always necessarily of the best quality. There's all sorts of problems around recording of alcohol consumption. These are from repeated cross-sectional surveys, but we know that people tend to understate their alcohol use. There's survey redesign going on in the middle of here, so this is not the truth about alcohol, and it's important to recognize that during the calibration process. What we've done as a starting point, because we're interested really in very grounded empirical calibration within a particular spatiotemporal setting, we're doing this in different US states, and we're doing it over quite long time horizons, because a lot of alcohol-related risks accrue over long periods. So for cirrhosis, we know that there's about a 20-year exposure window that's related to the risk of cirrhosis. So we need to understand how exposure changes over quite long periods. It's quite difficult to find synthetic populations that have been built for such long time horizons. A lot of the work has been for epidemic modeling, where obviously the time constant of the epidemic is quite short relative to the way in which people's networks change over time. So it's okay to use a static network. For these models, it's less okay to think of the population as being static, because we have much longer time horizons. So we actually imputed a new synthetic population for the US. In this talk, it's for the state of California. We actually have it for the whole US. Since starting in 1980 and pushing through to the latest census in 2010, obviously we'll update it when the new stuff becomes available. And it's microsynthesized from a number of different sources that meet the particular needs that we have on the project. So there's particular attributes of agents that we need, and we've imputed them inside. And this microsimulation is dynamic, so we also include migration between states and also migration in and out of the US as a whole. On top of that, we then layer some of the agent attributes that are of interest in terms of trying to explain alcohol use. And those differ by the different models that we've built. And the one I'm going to talk about is a model of social norms, but there's other theories that have also been discussed in the context of alcohol use behaviors. So things like social roles, the implication of being a parent, having to hold down a job, living in partnership with somebody else, and the effects that those have on drinking behaviors. People have looked at so-called social contagion, so selection and influence on networks. People have looked at behavioral economic theories, rational choice theories, motives-based theories. There's all sorts of theories that have been used to explain alcohol use. And in our project, we picked the 4 that have been used the most in the literature, and we assigned each of those models to a modeler, to a human. And in this case, our modeler was Charlotte Probst, and she was asked to answer the question, what would a social norms explanation have to look like to reproduce the trends that we see in alcohol use dynamics in isolation? Now, one of the hypotheses on the project is that none of these single explanatory theories will be sufficient. They may calibrate, but they probably won't validate. In fact, we also have problems calibrating them. But the overall aim of the project Cascade is to try to perform an integration of different theories to move to a more systems-based perspective. That's the promise. We're still some way from that. We've got about another year and a half to conclude that, but there's been a lot of infrastructure work, more than we anticipated. In the norms model, we have the notion of a reference group or an identity. In the version I'm going to show you, the identity was only based on 2 characteristics, gender and age group. We've now expanded that to a whole set of characteristics such as ethnicity, household income, educational status, and so on. And we can actually adapt that reference group as part of the calibration process to actually define its characteristics. Inside of the agent's heads, Charlotte, having read the social norms literature, she put these things inside the agent's head. So one is what she called payoff, which is some inherent desire that the agent has to consume alcohol. She's put in 2 perceptions of norms, a perception of an injunctive norm, so an agent's perception of what society thinks agents like them should be doing in terms of their drinking behaviors. Should they be an abstainer or not? Should they drink heavily or not? And also descriptive norms, which is an agent's perception of what's actually going on amongst other agents in their reference group. And then finally, the final parameter of the agent is something that Charlotte's called autonomy, which is the extent to which the agent just doesn't care about social norms, okay? So they might perceive them, but they still don't care about them. Okay? And in our agents, there's heterogeneity on the payoff, and there's heterogeneity on the autonomy. There's also a bit of heterogeneity on the perception bias of the individual agents as well in the model. The model is a multi-level model, so we could have implemented norms as influence mechanisms on networks. Instead, we implemented them as macro constructs here. So this kind of gets back into some of the discussion with Rob and other people earlier about how we should look at the ontology of this. So in our ontology, the injunctive and descriptive norms are represented as macro entities. Identity could be considered a macro entity, but the perception of it by the individual occurs at the individual level. That leads into a perception of norms, and then all of the other stuff ontologically is going on at the level of the individual. These agents are not connected on a network, so we might regard it as an individual level model or a microsimulation, but it is definitely multi-level, a bi-level model. In terms of how some of these, the dynamic mechanisms that have been put in place in the model, I'm just going to go through them very slowly. So one is the way in which that macro descriptive norm is updated, and that's updated based on the actual drinking behaviors of agents within the simulation over time. So this is a dynamic property. A second one is the way in which the injunctive norm is affected by the descriptive norm, and there's, what's been implemented is quite a gradual adjustment of injunctive norms to account for a descriptive norm staying around for a while. So if particular types of agents are drinking in the same way for a sustained period, then that acts to relax the injunctive norm in this representation. And the final one is what Charlotte called the binge punishment feedback loop in this, which is that if certain agents, certain groups of agents in the model start representing problematic patterns of consumption, heavy episodic consumption that's perhaps leading to hooligan-style behavior, as Bill would say, then society will perceive that and implement regulations and other institutional interventions to actually tighten that injunctive norm. So there's a kind of interplay going on between the macro and the micro level here, and that's what it looks like in its totality. At the individual level, the agent's really weighing up a balance between their own desire to drink and what they perceive of the descriptive and injunctive norms, and autonomy acts to weight this one way or the other. So if the agent has lots of autonomy, then they only care about their own desire. If they have little, then they only care about the descriptive and injunctive norms. And this is a property that's estimated as part of the calibration process. In terms of the equation that describes what's going on in the agent's head, this is what Charlotte implemented. So all of the things that you've seen, the payoff, the autonomy, and these perceptions of injunctive and descriptive norms are there. So the overall perception of the norm is a geometric mean of the two different types of norms, and the overall disposition to drink is a weighting of the payoff and the norms, where the weighting is the autonomy.
Convex combination,
Yeah.
payoff and social, weighted by us.
Yeah. So that's the base. And there was quite a lot of discussion as Charlotte was building the model about exactly what the form of this would be. And this was what I'm going to show is our most restrictive attempt actually to use inverse generative social science. And we focused just on this because there was quite a lot of debate about it. So we said, okay, let's throw this open to the machine and see what comes out of it. We've since gone on to extend this to cover the totality of models, and we've actually changed the way in which some of the methods we've used in order to cope with that as well. So what we've done is we've taken that equation and we've stripped it out into a set of primitives. So there's primitives in terms of the variables that are in there, and there's also primitives in terms of the functional forms. So we saw some addition operators, we saw some multiplications, we saw complement, we saw a square root, and so on. So we are constrained to a certain extent in terms of what any new model can look like by the human modeler's initial kind of set of building blocks that they use. And we do this in our other approaches as well. So we haven't escaped from the kind of bounding container of a particular human modeler's view of the building blocks.
And I think that's part of the art form will remain. How do you identify the building blocks that are really, germane and have some explanatory potential and not just superfluous?
Yeah. We start with a parameter calibration process, similar to some approaches that have been described in previous talks. So we use a Latin hypercube design experiment that's been optimized for its space-filling properties. We have quite a lot of parameters, 28 different parameters. We sample from those a large number of times, and we look at how well each of the models, after we've run it, compares to those time series that we've seen previously in terms of in this case, one of the goodness of fit metrics that's used in the approximate Bayesian computation community that they call an implausibility metric, which is essentially the difference between the time series emerging from the agent and the target time series from the NISDA data, normalized by the standard error in that data set and a discrepancy term, which here is described as a model discrepancy, so we're just admitting that there's some error in the model that we can't do anything about. It could also be a kind of discrepancy in the sample data as well, given the issues that we know exist with that time series. And then we're just summing that overall points in the time series and overall the different targets, the different types of drinking patterns as well. And we're calling that an implausibility metric. When we use that implausibility metric, we run that calibration process. In the end, we really want to do a proper Bayesian calibration, so we would expect to see posterior distributions here. All I'm showing you is the best fitting model. The model is in black, and the red is the NISDA data you've seen before. And you can see that we still have some issues with that. So the human-generated model, for example, is underrepresenting the levels of absenteeism in California in the later years of the simulation. So, we're actually struggling to get this model to calibrate in the first place. And you can see some other areas where there's kind of a persistent bias in this calibration. And what we want to know is, can we produce other structures that might offer us a better calibration than this? In terms of the model discovery methods that we use, we're kind of slightly constrained by the resources we have available. I mean, ideally, we would want to search over a large number of structures, and for each one of those structures, we'd want to perform a parameter calibration. We simply can't do that. We haven't got enough resource. And we're really interested in discussing ways in which we might improve that process. What we did in this case was we actually just left the original prior parameter calibration for all of the different structures. And after we'd identified a set of structures at the end, we then ran the parameter calibration process again. Obviously, that's less than ideal. It has thrown up quite an interesting result, actually, which I'll show you in a moment. But this is the overall process, so that the model came from the human expert. We abstract that structurally. We perform a prior calibration. We use that prior calibration along with the structures to perform an evolution, and then we post hoc do another parameter calibration on the structures afterwards. The method that we used in this case is a multi-objective genetic programming. The genetic programming is quite simple. It's a tree-based approach in this case. In other cases, because we did want to constrain some of what was theoretically realizable, we actually have moved to using a context-free grammar. So I was quite interested to hear some of the conversations earlier. So in the latest work, we use a grammar-based approach. In this case, we're using a tree-based approach. You can see some of the technical details of the GP process there. It's multi-objective. We work with two objectives. We work with this implausibility metric that represented the goodness of fit, and the other one that we worked with in this case was the actual tree size, so the amount of the size of the model that was being constructed, and we use that as a proxy for interpretability. Yeah? So the more trees that are in this model, the harder it's going to be for us to interpret it. It's not, and there's other objectives that you might think are important, but those are the two that we've worked with here. For implementation, the actual multi-level model is written in repass HPC. We like repass for a few reasons. One is that it's got continued NSF funding, so it's being maintained. Another is that it's written in C++, so we can do quite rigorous software design. And thirdly, it's scalable in terms of the number of agents. So we quite like repass. And in this case, we've hooked it up to ECJ, which I think is a George Mason Java-based evolutionary toolkit, and that's what's doing the multi-objective genetic programming side of it. Okay. In terms of what comes out, so this is what I'm going to show you here is a trade-off surface between goodness of fit on the horizontal axis and the model size on the vertical axis. The orange one is pre-calibration, pre-parameter calibration, and the blue one is after we've subsequently run a parameter calibration for each of those models. So you can see that in all cases, it will make the goodness of fit better. Obviously, it doesn't change the model size because we're just changing the numbers in the parameters here. You can also see some decay in marginal returns in terms of both in terms of complexity and in terms of how much you can get out of the post-hoc calibration. If we just focus on a few aspects of this one here. So this model says that the disposition to drink is just the agent's payoff. Now it turns out that payoff is initialized in a way that's correlated with agents prior drinking. That's how we initialize it. So all this is really saying is that past behavior predicts future behavior. That's the simplest model that we found. And then you can see that some of these more complex models have started to introduce some of the other concepts that Charlotte defined as part of her model. And we can already, when we get the tree size up to about 16, start to have to scratch our heads a bit to think about what some of the interpretations are. In other, not in this work, but in work that we did on our social roles model with a social psychologist, we kept returning to him as a domain expert with these trade-off surfaces, and they were bigger. We were talking about structures with 80 elements or so, and we had a fun time trying to interpret those with him. And a lot of the interpretation was that this is junk in theoretical terms. In that case, it took us 3 iterations with the domain expert and 3 iterations of further constraining the grammar, so kind of modifying the grammar in order to get the machine to produce things that the domain expert felt were theoretically interpretable. We got there in the end. We found 2, okay, in that other model.
The other nice thing to notice is in our elaboration, we did not give the machine the opportunity to just scale things linear, to do A times X. So we believe, we go back to
sorry, sorry.
that we think all this square roots within square roots of square roots of square roots is the machine struggling to learn how to just multiply by a number.
Yep, that's exactly right. And you see that, you see it in the very, very marginal improvements here. And yeah, the machine is trying to find scaling parameters to improve the goodness of fit.
Another incarnation would probably allow linear scaling.
If you look at these structures, you see that simple one actually doesn't calibrate very well. So you can see that implausibility metric, this is past behavior predicts future behavior. Actually, it doesn't.
Okay. Let me just interrupt with that last comment. It just made me realize, was there a reason why you didn't allow coefficients to just exist there?
It was just an early version.
Oh, okay.
Yeah, so in the roles model we do.
I thought maybe there was like a legitimate, like, we're like, no, this could not be this way.
So if you could actually just work without the coefficient, and then you can add the coefficients in, so you can fit a function and put them away.
Technically, you could get any rational number if you allow the number 1, and the concatenation's there, because any numerator is 1 plus 1 plus 1 sometimes, and the denominator is another 1 plus 1, and division is allowed. So you could get any rational coefficient. It's crazy to be adding 1 10,000 times or whatever it is.
Yeah, so we do have other strategies for that, but I'd be interested to hear, from you how to best do that. But it was
Funky too, right?
Sorry?
Squared. Yeah, squared is simple, right?
Yeah, so payoff is a number between 0 and 1, so that'll be acting to attenuate it. It'll be a scaling factor less than 1. So the goodness of fit of past behavior predicts future behavior actually doesn't. So you can see it doesn't fit particularly well. if we look at the ones that are best fitting, we've got a better performance, and it's better than the original human-built model. We still have some problems understating the heaviness of drinking per occasion in males.
So much volatility in the male model on the right.
Where here,
In the actual data, yeah.
that's the actual data, yeah. So
Does anyone know why that is? And
Yeah,
also,
zero
if you look at
recession
the
with-
data in the middle, the men and women inverts, where you have the
yes, yeah. I wondered if somebody would spot that.
Yeah.
We looked into that and we couldn't find. There's no obvious coding problem in the data there, interestingly, because it does just look like it's a flip, doesn't it?
It's weird, it's so inverted, yeah.
We see it also in the PSID data, so the panel study for income dynamics. There's a point where it also has this kind of strange flip in income. Interestingly, one of its core variables that it's measuring. Again, this is one of the core variables in the data. We've actually moved away from NISDA now, and we use BRFSS, which we also scale to sales data. So we've moved away from this as target data. It does have a number of issues, and obviously they have the target data you use obviously has major implications for an inverse generative approach. So I think it's another thing to ponder. Yeah. So this was where in the talk that effect modifier came up, but we've spoken about that. So in conclusion, we're enthusiastic about this approach. We think that it's got a lot to offer. We found that looking at the trade-off between those two aspects of an overall model's worth was interesting and brought some insights. Some open questions, and a lot of these came up in the discussion at lunchtime anyway, but how do we perform an efficient search in these conditions where we might have under-constrained spaces? What other criteria are important? As I say, that really came out in the roles model where we started working with a domain expert. It became clear that there were other beliefs, if you like, that ideally we would want to account for in the process. And is this scalable beyond what we've looked at here in norms to a wider consideration of theories? And again, I think that came up as part of the fifth discussion over lunch. That was interesting to see. To do that, our ambition really is to develop a whole library of theory components, rather like the idea of having grammars for particular situations. To do that, there is going to need to be some kind of consistency in representation in how that's done. And I think Ivan as well kind of raised that, the idea of having some kind of common schema that you could use to represent different types of mechanism. So, then we end up with a calibration process that isn't just a classical one in terms of inputs and parameters, but also allows you to search through this wider library when you perform the discovery process. So Ivan also mentioned the idea of having a common mental model. That's something that we've explored in our project as well, given that we have 5 different postdocs making different models, as well as a set of investigators. The one that we used in the particular project, we used an analytical sociology framework that was a multi-level approach. Josh doesn't, he gets a bit agitated when I talk about the Coleman boats, but for those of you familiar with middle range social theory, that's the type of framework that we're using. We turn that into a software architecture. So we use a mediated object-oriented design pattern to create an abstract software architecture that we then realize in C++. And so our modelers, they're working with a common, essentially, architecture that allows us to actually do searching over lots of different components because we've got that commonality. What the individual modelers have to do is inherit from this base agent template and from these base structural templates, and they have to fill in these things here, do situation and do action, and do transformation, which is the aggregation operator. They have to write the internals of that. So for us, any particular mechanism-based component always fits within that schema. And obviously that's limiting because this is one particular framework. It may not suit everything, but it's the one that we're working with, and it fits all of the different approaches we've looked at. We can also do selection and influence on networks using this, although it doesn't look like a archetypical agent-based framework. But it seems to work okay. And it has an epistemological, or several, in fact, epistemological perspectives. Where's that left us in the end? There's been quite a lot of infrastructure building, so this is the bit that we've done. So we created this abstract software architecture based on middle range theory, and we tagged alongside it a microsimulation of the US population from 1980 onwards that allowed us to do calibration within particular spatiotemporal settings. On top of that, there's the theory itself, so our modelers have built particular theories using the architecture. So this is all our stuff. And then under the hood, we're relying pretty heavily on repast HPC, so our architecture links directly to that and is dependent on that at the moment. And underneath the hood, we're typically, we have explored running on large HPC clusters, but given our inability to properly plan when we're going to need large numbers of cores, in fact, we've bought our own standalone boxes, and we typically run our calibrations on two 38-core Intel i9s, which are pretty quick, actually. And we can use them all the time, and we just flog them completely. And we look at scale-up. So we want to actually run these at scale, one-to-one scale in the end. We run them at smaller scales. So we normally run with about 1,000 agent populations for the purposes of the calibration, and we look at scale-up effects. So we're continually looking to see whether or not, when we scale up the population, is it impacting qualitatively on the dynamics of these simulations. And that's it, really. So I just need to acknowledge the wider team. So obviously Josh, myself, we also work with the Alcohol Research Group out in California and the Center for Addiction and Mental Health in Toronto, and it's we're in year 4 of a NIAAA funded R01. Yeah. Thanks very much.
Oh, I have the mic. That's it. So like whenever there's like a modeling fit issue, usually, for me at least, it's usually a data source issue, like the data you're using to predict an outcome. Like were you ever using like geography stuff, like how close somebody was to a liquor store, to a bar, like all that?
Not as part of this model.
Okay.
So there is another model that was developed by Pacific, I think it's there is a group looking particularly at availability and the spatial availability of alcohol and the link to violence. And there's actually an agent-based model. I think it's Gorman et al. That looks at that in the American Journal of Public Health. That isn't included actually in our set of theories. But obviously that's, in the end, that library, what I'd like is to get all of the different potential explanations and get them in there.
Then you could just weed it. You could weed it down from there. You
Yeah.
might as well have that. Just really build out the database as vast as you can with things that probably won't be strong indicators, but because you find sometimes you just find like the weirdest things happen to be, like that the fact that like somebody lives 5 miles versus 15 miles from a bar and they're sitting at home. It's like, oh, I'm not going to go to the bar tonight. But that 5 miles, all of a sudden, it's like, well, I could go for 30 minutes, right? It's like,
so some of the economic factors.
Right. Or like jobs stuff, yeah, exactly.
I'm just curious, say you didn't treat it as a time series prediction problem. Say if you took all the data and you just fit the data, and you looked at all the models that fit the data. Maybe you'd get more, I think your data impoverished a little bit, right, with respect to the time series? Or are you okay? like, you say you fit, why are you bothering to predict? Why don't you just fit all the data and then look at all the explanations for the data?
I think, so there is a reason for that. So the reason is that I think we accept that the mechanism-based explanation isn't a set of universal laws about what drives drinking behaviours. They're contingent in a way. They're contingent in a spatiotemporal setting. So so what we wanted to test by reserving some of the data for validation is whether or not the mechanisms that we've identified using a particular temporal setting and spatial setting would hold in a different one. We could do it. We could do it by looking at different cases as well. So you could look at California as a case versus New York State. We are doing that as well.
Yeah, because it wasn't clear where the temporal spatial information really was in your data.
So this is state level drinking patterns.
Yeah.
Yeah. That is the
People's
data.
age, but it's not where they live, and it's not spatial, and it's not temporal. It's like, why did we not? I mean, is there actually a temporal dependency on this or not? If it's not, it just happens to be not related to, you know, something causing people to change their drinking habits over time, then you could predict any part of that time series from the rest of it. I don't think it's a temporally driven time series. I think it just happens to be data you collect every year. That's what I'm suggesting, right? Take the temporal causality out of it. Like, did I drink more in 95 than 94? I don't think that's it. I don't know why, unless you can tell me, oh, I could see in economic conditions, so we all had more money in 95, so, or it was really bad, and, you know, we all went to the bar because things were economically terrible. I'm just wondering, like, why you have to treat it like a time series, as opposed to just like bucketing it. It happens to be convenient that you have it in units of temporal units, but I'm not sure if there's any time dependency.
I'm not sure, I mean, I guess
Because if I try to treat it like a time series, then what I'm saying is what I did at T-1 matters, what I did at time T. I'm not sure does the data, I mean, is that what people, experts say?
There's quite a lot of, so particularly some of the theories around, the behavioral economic theories around what you might call addiction, or, you know, there's the idea that people accrue reservoirs of, maybe they're not sensitive. You know, if I drink, if I stop drinking for a few weeks and then I have my first drink, I'm going to feel more intoxicated than if I carried on drinking, you know. So there are, I think there are temporally relevant dynamics at the individual level, and certainly people would represent them in that way.
Are you suggesting that we just take the time series on and out?
Chop it all up.
What? Take
chop
every
it all up in
person, every
buckets.
drink?
Yeah.
Sorry? Then it's just a number, right? What,
Yeah.
is it just a number?
We'll just fit it all.
I'm sorry?
I'm not sure what I'm saying.
But I'm not sure that, I was actually thinking about it.
People times total drinks integrated over 50
If you
years,
actually
it's
looked
just a number.
at US addiction, and then you hit opioids, what happens? Well, doctors actually started prescribing stuff that they didn't know was addictive. And pharmacy companies started supplying doctors with promotions to help them do that, you know, blah, 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 blah. There was all this causality in it. But how much of that causality, there were certain things that have to appear in certain order, but they didn't always have to. The fact that it happened in 1995, did that make a difference? I'm not sure. That's all I'm saying, is I'm not sure why someone's drinking today. It really depends on what they did yesterday.
But that's the idea of the model. It depends on what your social group did yesterday.
Right,
and
but
what
you're
you
trying to predict a time series.
regard as acceptable and not. And
Yeah, no, I do understand that, but then why are you predicting a time series?
Because you're making decisions on a daily basis about whether to drink and how heavily to drink. And it's the sum total of those individual decisions.
So are those dots daily dots, or are they annual dots?
Sorry?
Are those dots daily or annual? I thought it was annual, so you're not making a decision every day. You're making a bunch of
So the
decisions.
agents do. The agents make daily decisions about whether they're going to engage in a drinking occasion.
But
And
they will
actually,
do
they make next drink. In the model at the moment, they actually decide to take the next drink. So it's, you know, conditional on being drink. So the agents are taking per drink decisions. The data points relate to the target data, which is a repeated cross-sectional survey that's available every year.
Right,
Yeah.
so it's not actually temporal. I mean, it's reported every year, but it's not about temporal behavior.
There's a,
I mean,
It's-
it's
yeah.
at a different abstraction level, right? It's year to year, not day to day. That's all. For some reason, that just didn't feel consistent to me, but there's an abstraction change there. That's all that struck me.
Well, get one more question, then we should probably.
Yes,
So I was also.
I did very fast. So horrible. So in the data set, I know that you have data set for many countries, many states.
Yeah.
So in some of them, is there a trend component going up, going down? Because some of the graphs are very there's no trend. So is this random noise, or is it really something important like the up and downs around the trend line, which is zero slope?
Yeah, I think that it's both. So there are trends in the data set, but there's also a degree of not just noise, but potential bias. And so we've worked particularly with CAMH in Toronto to try and improve the quality of the target data set. So that's very, very recent for us. So we've only just gotten a first release of what that looks like. So that's worked with synthesizing a number of different observational sets around alcohol use to try and get better grade target data. Yeah. So the stuff in the NISDA is sufficiently worrying that we've moved away from it. Yeah.
This is also quick. So, given that you studied basically like 40 years of data, I was wondering your opinion on. So why do you try to fit one model to all people? So basically, I imagine that generation after generation, and that's why you're maybe at the year 2000, your population is probably totally different from 1980. So why don't you assume that people can change, that the generations can inherit a new model? And how do you think about that?
So we do assume that the agent's structure is the same throughout the simulation. I mean, obviously their parameters vary. They are heterogeneous agents. I think that's a good point, and perhaps could be going back to your question around how to use the data set. That could be one of the things to do, would be to try and bound that.
Yeah. Overlapping generation.
Yeah. I think that's a good point. Yeah.
The attitudes to change.
It could be like an interaction between time and economy,
That
right?
would be reflected in the.
So like with the economic conditions and time.
You're saying over time.
Right.
Yeah, I think we need to see care between the parameters, which can vary quite a lot between the agents, and whether or not the structure changes is the real question. But I think it's a good point that you raised, and perhaps helps answer the question, Uname's question. I'm not sure. Yeah. Okay, thank you very much. Thank you.